This is my third lecture, and this is sort of largely based on this as well as this. All of these other references I have already given you, so you know about them. And the Keeling and Rouhani reference I call K and R, and I will refer to it whenever I use a figure from there or a program from there. These are the other references that I gave you, which you can't see. What I want you to do is to, so Keeling and Rouhani have a book, which is this book, and they have a lot of computer programs that are part of that book. These programs are downloadable from the following site. This is homepages.warwick.ac.uk/mafsfz, blah, blah, blah. And this is a page, so you can see program 2.1, 2.2, 2.3. All of these connect back to parts of the text. And over here, the files you can download are C++ or Python or Fortran or MATLAB, etc., etc. So I assume that by now, all of you will have installed at least one. There must Python or a C compiler or something like that. Those of you who don't, there are some that are already located on that. There is certainly Python installed on those desktops at the back. So we will look at some of these programs probably on the last day, but I can urge you to first download some of these in your favorite language, whether it's Fortran or whether it's Python or whatever it is, and just check that they work, that you are able to cut and paste the code into a program and run the program. You can copy this from here, or you can just do the following, which I did, which is just type Keeling and Rouhani into Google, and this is the fourth entry when I type it in. So that's web pages contain all the programs labeled in the book, blah, 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 generally available, etc. This is the same link that I gave you in the previous page. So this is the cheap way of doing it, but for those who have copied the link, they can also do it that way. So just remember Keeling and Rouhani. So we've done background to disease models, the SIR model, and what I want to do now is the stuff that I didn't finish up the last time, I want to spend a little bit of time doing today. So for example, what are related models to the SIR model? We'll go over the SIR model again. What is the role of vaccinations? What is the role of herd immunity? How do oscillations come up in this model? How does one think about this in a dynamical systems way? Okay. No laptop problem working. Okay, hopefully that won't happen again. Okay. So let's start by reviewing. And the reason I'm going fairly slowly is that I would like everybody in this room to keep up with me. None of this mathematics is very difficult, it's straightforward. The ideas are a little more complex, and the development of these ideas are a little more complicated than just doing the mathematical calculation. So to remind you, we have in mind something where there is an individual who is sick, who is well here, sick here, and well here again. So this individual is susceptible initially to the infection, is actually infected, and then has recovered from the infection. There is two parts to this. One is the individual's experience of their illness, which typically is just in this region here, when they say that, look, I'm actually feeling ill, and I'm able to infect other people. And the other is the dynamics of the microorganism within that person, whether it's a virus or a bacterium, that sort of starts out small, begins to multiply, rises to a maximum, and then comes down again with a tail. Once this drops down below this a certain value, it can sort of depend upon what your conditions are, how infective you are, then the person can no longer transmit the infection to other people. Okay? So both on the increasing side, up to this point, this person is not, although he or she is infected, and therefore it's in the exposed, has already been exposed to the infection, until this point that person cannot infect other people. Similarly, after this point, the person cannot infect other people, even though the dynamics of the bacterium or the virus is going on in the background. So as we said, we're going to think about this in terms of compartments, the S compartment, susceptible, I compartment, and R compartment, which describes the nature of the health of a group of individuals. We are not going to account for the fact that individuals are all different, they have different susceptibilities, they have different ages, they have different exposures, etc., etc. We are just going to say that anyone who is susceptible is in this compartment, anyone infected in this compartment, anyone recovered is in that compartment. And as I said, these dark lines, these dark arrows mark the transitions between these compartments, and the dotted arrows mark the influence of one compartment on another. Then we mention the force of infection, and the force of infection is defined very simply in the following way, that the number of susceptibles goes down in time if the susceptibles are exposed to some infectious agent or somebody else who can infect them. All of that is in one parameter called lambda. Of course, the number of people who become infected and therefore move out of the susceptible compartment must be proportional to the number of susceptible people in the compartment itself. Okay? If I have 100 people, maybe 2 will get infected. If I have 1,000 people, maybe 20 will get infected. So, there should be some simple scaling between those numbers that is really involved in writing something like this. Then the second assumption is that what is the form that lambda can take? We know that lambda must involve I, the number of infected people, but does it involve that number itself? And there is a proportionality constant, lambda is proportional to I, but for lambda to make sense, you should put some proportionality constant here, which we will call beta, and say lambda equal to beta I in this case. So now the question is it proportional to the total number of infected people in the population, or is it proportional to the fraction of infected people in the population? So that's this assumption versus this assumption. So this assumption is called frequency dependent transmission, this is called density dependent transmission. And as I said, most people now think that this is the appropriate form that one has to take when describing a disease. So if you remember how we discussed this, we said we could make this argument depending upon how we expect behavior to scale, and the fact that the number of contacts don't increase as you make the population size more. That you just, if you change your population size from 1,000 to 1,000,000, you just don't talk to that many more people. You're talking to pretty much the same 20 or 30 people every day. So that's the intuition that goes into that particular statement. Then we wrote out a form for assuming frequency dependent transmission for how the number of susceptibles changed in time. So there was proportional to S and proportional to I by N, and this is the beta factor that I told you about. So this now tells you how many susceptible people, how do the number of susceptible people change in time, and this information is all, the rate at which that happens is contained in one quantity which is called beta. After this, the second assumption that you make is that those infected will recover at some rate. So those in the recovered box, in the recovered compartment, their numbers will increase, and their numbers will increase at the same rate at which people are leaving the infected compartment, because overall whatever leaves the infected compartment can only go to the recovered compartment. Okay? Are you all with me so far with this? Now we take all of that, put it into a set of equations, and here we have done one scaling to get rid of the factor of n, that is just define S equal to S by n, I equal to I by n, R equal to R by n. So S plus I plus R equal to 1. Once I do this, then that is what these equations will look like. Notice that these actually look exactly like the equations that I would have written down for density dependent transmission. It is only that my interpretation is different. Over there, if I assume that these equations have the same form, then S, I and N refer to the full numbers in that population. But over here, they refer to the fraction of numbers within that population, even though these equations look the same. So that's where the difference actually is. And this is called the SIR model, and S, I and R must always be less than or equal to 1 and greater than or equal to 0. That's a condition on them. Then we said, okay, let's take this model. This is a sort of linear, it's a linear differential equation in time. These are nonlinear terms on the right hand side, and varying the quantity beta, you can ask what is the behavior. So then we said, okay, just looking at these equations, we can say that there seems to be some threshold value. For values of beta that are small, then even if you start off with 1, 5, 10 infected people there, that number will come down in time. If value of beta is large, in this case larger than 1, the number of infections rises initially before reaching a peak and then coming down. Okay? And that is the behavior of these coupled equations here. And in order to understand that, we said, okay, let us ask what happens if I take a population in which almost everyone is susceptible initially. In that population, I introduced one person who is infected. Now, if the population is large, then these S's and I's are pretty much continuous variables. So I can say if I have a very small value of I here, and an S value that is very close to 1, how does the number of infecteds change? Having written that down, you can see that this depends upon the sign of beta S versus gamma. Now S equal to 1, so it's really the sign of the magnitude of beta versus the magnitude of gamma as written out here. And that really comes down to the fact is beta of gamma is greater than 1, infected numbers will grow. If it's less than 1, the infected numbers will come down. And this is the important quantity in this equation, it's called the basic reproductive ratio. So all of this has been just background so far. Okay? You're all with me on the background, you've understood these equations, you've understood where they came from, what they mean and so on. So let's go on to discuss some more technical properties of these equations, and that's called the phase plane. So this sigma is the same as R naught. Remember, I had a bunch of different definitions for average contact number, basic reproductive ratio, reproduction number, etc. So we said they're all equal at the same initial part, and if I'm only talking about the initial part of the epidemic, then typically sigma and R naught are the same. So that's just a change of notation in this particular book that I used it. And so these are what are called phase plane trajectories for this equation. Over here I have susceptibles S divided by N, infective I divided by N. So that's a fraction. So these can go only between 0 and 1 and 0 and 1 in this case. So what is this and what does this tell us when we write something like this? So remember that the solution to any set of differential equations is some family of functions. Okay? And you can choose two variables that you're being solved. Suppose x dot equal to something, y dot equal to something. I can plot my x here and my y here on this side, or in this case p and q. And then I can say if I start at a particular point, where do my solutions go? All right. So if I took, for example, this particularly simple linear set of equations, dx by dt is ax plus by, dy by dt is ax plus dy. All of the properties of these equations are contained in a, b, c and d. And as you know, even more important properties of these equations are contained in the determinant p squared minus 4q that enters here, because these determine the eigenvalues of this particular linear transformation on x and y that tells you where are x and y going as a function of time. So these are different regions where delta greater than 0, less than 0 inside here. And in the case where delta is less than 0, you wind up with stable fixed points. You sort of move into either in a spiraling fashion here or in a circular fashion about this particular point. But over here you typically move away from points, except from isolated points here where, for example, this is a saddle where you move towards this point here, but everywhere else you tend to move away. Okay? So just by knowing what is p squared minus 4q, you can ask about any one of these points, what is the sort of behavior of trajectories, and that's the whole idea behind phase plane. And the vectors that are drawn here represent derivatives. Which direction will you move if I start at a particular point? So these are equivalent points of a linear autonomous system. And now we can go back to our SIR equations and ask, how do we understand that particular behavior? So remember that we start with S naught, S at 0. So now I'm going to imagine that I multiplied everything by n in my head, all those numbers. So now I'm actually talking about the full numbers, susceptible full numbers of infected and so on. So if S naught is S naught greater than 0, I naught is I naught greater than 0, R naught is 0. So I have some susceptibles and some infecteds. Okay, here are my equations. I can look at these equations and divide one equation by the other. In this case, I divide di by dt by ds by dt. So this term and this term will cancel with a minus sign here. I will get I divided by beta s below, gamma divided by beta s, sorry, that particular term over there. So now I have di by ds is minus 1 plus gamma by beta s. I can now integrate this equation to get 1 I plus s minus 1 by r naught log s must be a constant. Okay. And I can write that constant as I naught plus s naught minus 1 by r naught log of s naught if I wanted to. It does not matter, just as these equations are constant along any trajectory. Yeah. R is r at time t equal to 0, so there is no recovered. This is the basic reproductive ratio, because that is the beta divided by gamma that turns out. So that's why I wrote it in a bracket there to say r at t equal to 0. So now I can do this. I can start just below 1 at 0.99. I can start with I0 at 0.01, and then I can plot my trajectory as it goes from here and then finally lines up here. So at this point there are no infecteds because that's gone to 0 here. So, even though I started off with a very small number of infected people, a small infected fraction of 0.01, I have managed to go back along this particular trajectory where S and I both change up to this particular point, and this is what the trajectories look like as a function of I and t as a function of time on the x-axis. Okay. I can do this for different values of beta. So, beta equal to 0.2, 0.3 and 0.4 with gamma equal to 0.1. Remember that the only useful combination of these variables is beta divided by gamma. So, beta divided by gamma is 2, 3 and 4 in this particular case. Again, I start from this particular value and then I ask where am I going. And as you know, you start here, go this way and you peak in this value. You have more and more infecteds as you increase the value of beta. And this again we know because we know the different plots for SIR and for SI and R as a function of beta, which we've already shown you in a few slides earlier. So, now I can take this and plot the whole phase plot in the space of S's and I's, and you can see that this tendency to sort of come here and then go back down is actually explicit in these family of curves, these family of vectors that I've actually seen, that actually come from this quantity here. So, here is the existence of the threshold value at this point. That is a point where di by dt must be 0, and di by dt is 0 if S equal to gamma divided by beta, and gamma divided by beta is known as 1 by R naught. So, value of S at which of 1 by R naught, if I start at that particular point, then the I does not change because it is only pointing in that particular direction there. Okay. So, that is the same idea extends to this particular idea here, saying that look, if you are on this side of this line of the null climb, if you start with acceptable numbers that are small enough here, then the curve always moves backward, it always decreases in time. If you start here, it comes down. On the other hand, if you start with larger number of susceptible people, this is the 1 by R naught factor that I showed you there, then this curve goes up before finally coming down. So, that is the distinction between an epidemic and not an epidemic. Remember, it just says that, except it is written in a slightly different way. We have always been thinking of a fully susceptible population in which we introduce one infected person, but this just says that look, even whatever susceptible proportion you start with, if you have a beta divided by gamma, what is important is the 1 by R naught and where that 1 by R naught lies in the space of the susceptible fraction. For small susceptible fractions, you will always go down. For large susceptible fractions, you will go up before coming down, and this increase before finally coming down is what is an epidemic for us. Okay. This of course is called a null climb. Let us now ask, so are we clear so far about how to do the phase plot for these equations, how to interpret them, how to understand them? It is all very simple mathematics, there is nothing complicated about this. Let us now come to the question of why should we vaccinate? If someone has a disease, why do we say that look, let us vaccinate people against diseases before they get their disease, so that we may then protect the rest of the population, protect not just that person, but also other people from that disease. Let us just start with this particular term here, di by dt is beta S minus gamma times I, and we know that if you have S less than 1 by R naught, then your epidemic will come down. So, that we know because we have just done that. We have said that if we start with number of susceptible people that is smaller than a particular amount, in this case 1 by R naught, any sort of initial value of infected people here will always come down. Even if I had so many infected people here, this will always have to come down. People will get better, and the number of people, fraction of people infected in the population can only go down and cannot go up. Because you will see that this is a natural boundary here, this line here, because S plus I cannot be greater than n on its own. So, that is in this case it cannot, the sum of these quantities has to be equal to 1. Therefore, they must, all these curves must fall below this line, that is the only physical part of this curve. So, now since we know this, we can say aha, S has to be less than 1 by R naught. So, suppose I take my initial S and I now begin to vaccinate some fraction of them, let that fraction be P. Then the number of people left who are susceptible, who have not been vaccinated, is S into 1 minus P. If P is 0, everybody is susceptible. As I increase P by vaccinating people, S will go down. Okay. So, now if I change S to S into 1 minus P, then R itself must change, because that threshold value that that marks the null climb will change by this particular factor. Okay? It's exactly going back to that system of the phase plot that I showed you. Once you do that, then you know what to do. You know that what is important is to reduce R naught, the effective R naught, below 1, because beyond that point no epidemic will propagate inside the system. So then that reduces to the question, what should P be for this quantity to be less than or equal to 1? It's a half a line of algebra to actually check that the critical fraction of people that you must vaccinate, that you must immunize against a disease, thereby making sure that the number of susceptible people is reduced, is related to R naught as 1 minus 1 by R naught. Is that clear what that is? Of course, this makes sense only for R naught greater than 1, otherwise this would not make sense as a equation, and that is required by that particular requirement there. But now you can see that as R naught becomes bigger, the more and more people you have to vaccinate. So, as I said, Ebola R naught was 2. How many people should you vaccinate so that the population is protected against Ebola? What fraction of the population should you vaccinate? Half the population you have to vaccinate, exactly. For measles, which are not equal to 18, how many people do you have to vaccinate? 1 minus 1 by 18, which is approximately 1 minus 1 by 20, which is approximately 1 minus 0.05, which is about 95%, roughly speaking. Maybe so it's a little bit more than that. So that's interesting, because it says that depending upon the disease, upon how infectious is the disease, how easily it propagates from person to person, which is encapsulated in this value of R naught, there is a certain critical number of people in the population who you must vaccinate or immunize. People use these terms equivalently. To immunize against a disease is to vaccinate against that disease. Okay? The larger the R naught is, which is why vaccinating against measles early enough. We'll come back to this again when we talk about why certain diseases turn up in childhood more than they turn up in adulthood. But which is why ensuring almost complete vaccination of young people against measles is important, and is not so important for a lot of other diseases which much smaller R naught. For example, a universal AIDS vaccine is probably less important, because AIDS R naught is 2, and again 50% of the population is enough. You don't have to sort of hunt down every person and make sure that they get it. But for measles, mumps and rubella, it's important to actually do that. Okay, second point. Notice that there is something interesting about this. In order for the disease not to propagate, what we need is we need to drive the effective R naught below 1, for which we need to vaccinate some fraction of the population against the disease, which effectively reduces the number of susceptibles. That's the logic that we have been following so far. It's the logic behind this. What happens to the other people, the people you have not infected? How, why is it that they don't seem to be able to catch the disease, at least in this particular description? That's related to something called herd immunity, and the whole idea here is the fact that vaccinating a sufficient fraction of the population, not everybody, is sufficient to protect the whole population. So this would be the argument behind why the critical level of vaccination that you need, which is critical level PC, is not 1. It's not everybody in the population that you need to vaccinate. The fact that PC is less than 1, although depending upon R naught can be close to 1 or somewhat further away, it's a function of R naught. The fact that it is not equal to 1 suggests that people who are not vaccinated can be protected against a disease if sufficient people in the community are vaccinated. This, of course, you should not think of this as something that applies to you or him or you. This is a statement about populations, a very general mathematical statement about well-mixed populations and how disease is transferred to the other. So, if you are in contact with someone with measles and you have not been immunized, you are almost sure to get it. It's not a statement about you as you, it's a statement about populations. Okay? And that's important to remember. So, this is a particularly important idea called herd immunity. The creation of herd immunity through vaccination campaigns is central to how we think about how to protect people against disease. Are we clear about this? This is a very simple argument. As I said, vaccinating sufficient numbers in a population yields herd immunity. Here's the history of vaccinations. 1798 is smallpox, 1882 is rabies, all of these come, these are all sort of important breakthroughs in our understanding of how to protect people against disease. The rotavirus is important. People in CMC Vellore have been involved in understanding and developing new forms of rotavirus vaccines against children. And Lyme disease, etc., all of this. This is also an important one, the papilloma virus. And this is just sort of background information. Of course, in the West, there have been regular influenza vaccinations that have gone on. So every year, the CDC in Atlanta develops for the US a specific vaccine that is taken from combinations of various strains that are known to be circulating in that particular year. They prepare a vaccine and then they try to ensure as many people as possible get it. Usually the people to protect are the young people and the old people, because usually people in middle age, who are neither young or old, have sufficiently strong immune systems and prior exposure to protect them. But the young who have less developed immune systems and the old who are often immune compromised are the people in need of some protection against this particular disease. So even the question of who to vaccinate for optimal health benefits is also a question, because remember, this is a multifaceted problem. Vaccines cost money. So often it may not be economically sensible to vaccinate the whole population. So you have to make a decision. Are you going to vaccinate some people who are most at risk first of falling ill, and then ensure that their herd immunity may carry on to the other people? Okay. All right. Since we are clear about that, let us now try to understand the fraction of the population that is affected by a disease. So let us try this old trick of dividing one variable by the other. Let us divide ds by dt by dr by dt. So it is dividing this by this. So that gives me beta by gamma times s, because the i's cancel inside, which is minus r naught times s. Okay. I can now integrate this equation. It's the same trick. Log s minus log s naught is minus r naught times r, and therefore I can write the solution to this as s equal to s naught exponential of minus r naught times r. I can put in factors of n if I wanted to over here, because r could be replaced by n if everybody is recovered. I can make a bound. The s infinity has to be between 0 and n. R infinity has to be n minus infinity, because there are no infected people at infinite times. So I can take this and say that, look, at infinite time, s infinity and r infinity are connected through this following equation. That's really taking this, putting it here. These are all functions of time, but saying what happens at infinite time. Where do these solutions go? I can write this because I know no one is left in the infected compartment. Everybody who could have been sick has fallen sick and then recovered, and there is some fraction of people who have not fallen sick at all, who are still in the susceptible compartment. So they are either susceptible or they are recovered, but no one is infected at t equal to infinity, at infinite time. Okay. Then I can write this in this form as either n or 1 minus s infinity, depending upon how I normalize my numbers. There is unfortunately no way of actually solving this equation. So I can take, rather than I can write 1 minus s infinity and take r infinity equal to 1 in that particular case. But this will actually tell me what is s infinity. What is the number of people who are susceptible at infinity, at infinite time, after the infection has run its course. Why do I need to know that? Because 1 minus that number are the number of people who have gone through the infection and have later recovered. This s infinity here are the people who still remain in the susceptible compartment. So 1 minus s infinity are all the people in the recovered compartment. That means they are people who have been infected, because they had to be infected in order to reach that particular compartment. So you can do this and essentially find the fraction here for differences calculated for r naught equal to 2. Here this is the curve as a function of the basic reproductive ratio. That's a fraction of infected. You have to do this graphically, because there is no analytic way of solving this equation, and that leads to this curve that looks like this. As a function of the reproductive ratio, this is the fraction of the population that is actually infected once a disease has run its course. Okay? So you can say that if I have a basic reproductive ratio of 2, then the fraction of people who are infected in the population of the disease has run its course is around 80%. If it's 3, it's even larger. It's probably somewhere closer to about 92% or something. And by the time I get to the really large R naughts, this curve has pretty much saturated towards 1. So the larger the R naught, the number of people who have passed outer susceptible and become infected, that fraction has become larger and larger, as is expected, because you also know this because of the peak of that curve of I of t as a function of t, which we wrote down. If you remember, let me just go back there to that. If you look at this equation here, it's the fraction infected, this number is actually going up like that. Now, I infinity is the integral of this curve, it's the total number that is infected. So, this is number infected at this time, at this time, at this time, at this time, and how it's actually changing. Okay. Okay. Let's now do a little more sort of mathematical tricks with this. And dr by dt is gamma times I, which is gamma times n minus s minus r, as we wrote down earlier, which is gamma times n minus r minus s naught exponential minus r by r naught, just putting those terms inside. So, now whenever I have an exponential here, there is always some, I feel obliged to maybe expand that if I can. And the if the epidemic is not too large, you can expand this particular term that sits here. So, s naught e to the power minus r by r naught is written at s naught into 1 minus r by r naught plus other terms that appear. So, if I do that, I remember these, I am expanding this equation here, then I write dr by dt came from my previous equation, which came from here in this form, expand it out here, collect terms. So, there is gamma times n minus s naught from here plus r into r. So, this minus r becomes r into minus 1 here. The r naught s naught comes from this term here. I just collect stuff and I write it out. And finally, I have something that looks like this, which is dr by dt is constants times something function of r times something times r squared plus higher order terms that I have neglected, that I have forgotten about. Okay. This equation, as it turns out, as written, can be solved, and if you solve it, you wind up with an equation that looks like this, that tells you what is r as a function of t. You might think that, oh, you told me I did not have an analytic solution for I, r and s as a function, but there are lots of approximations that I have gone. In general, I have no, it is only valid in a limit in which you can expand r times r naught, exponential of minus r times r naught in the first few terms that it has. Here is the value of alpha, and here is the value of the phase factor, tan hyperbolic something. Okay. Now that I have that solution, I can sort of put it together, simplify it a little bit, remove the phi term, etc., and write it in this particular form. So, this involves the r naught, this involves the initial susceptibles, it involves a gamma, it involves a quantity called alpha squared, which we saw earlier, and this is sort of the phase factor here, and this is how the time behaves like. This formula is actually what was plotted by the original SIR model people, who were Kermack and McKendrick. So, they did not, this is the 1920s, they did not bother to solve things on a computer, but they were being, as I said, Kermack was a very clever mathematician, so he probably worked this out in his head, worked out what this form should be like, and found that this is what the peak was. So, this approximation actually does very well in this particular case, because the epidemic is not particularly severe. So, expanding exponential of minus r by r infinity does make sense, and you can see how well it actually does. Okay. So, that is an analytic solution of the model in a particular limit. Are we clear so far? Can you repeat that calculation if you try to? It takes a little bit of work getting that solution, it is not completely straightforward, but now that you know that it can be done, maybe you should try it out and look at what were the ideas that led to that particular solution. Okay. Now, let us make the SIR model more and more complicated. The whole business of thinking about epidemic models is to start with simple models like the SIR, and then introduce more and more levels of realism into that model. Say that I did not account for this, I did not account for that, I did not account for something else. We want to add them piece by piece into the original model and wind up with a more complicated model that is more biologically realistic. Okay. So, let us just introduce the first complication into this model, and that is called the SIR with demographic terms, sometimes also called vital dynamics. So, it is SIR model with the vital dynamics. Vital, vita means life. So, sort of it really means with the dynamics of life and death put into it. This is what these equations look like, the SIR model with demography. Notice that there is a factor of mu that enters here, There is now a factor of mu s that enters here, a mu I term that enters here, and a mu r term that enters here. That is the changes. If I rubbed out this term, this term, this term, and this term, I would have the original SIR equations. So, what do these terms mean? What is their interpretation? First of all, just imagine that we don't look at this. This term here, ds by dt equal to mu, says that S increases at fixed rate, which is mu. Okay? ds by dt is mu. Mu has the dimensions of 1 over time. The solution S is mu times t. Therefore, mu is a rate at which S increases. It is ds by dt. Okay? Whose is this? Is this one of yours? Vasanora. So, if that, so then what is the interpretation of mu? Can you, have I given you the answer? No, I have given the answer. The answer is births, because people who are born at rate mu are born into the susceptible compartment. Okay? The other part to it is deaths, and we assume that people can die at equal rate from here, and here, and here. So, if we now rub out this term, and this term, just having the mu terms there, the last mu term, that says the number of people, the change in the number of susceptibles in a small unit of time as a consequence of deaths is mu times that number. Okay? So, this is people being born, this is people dying. Now, add these equations up together. So, as you remember, these equations initially were written down for a very specific way, by which this cancelled, if I added this up, this cancelled this cancelled this, but now I have extra terms. I have mu here, I have minus mu s, minus mu I, minus mu r. However, if I plus s plus r is 1, then this term is exactly cancelled by this term. So, this is a specific limit in which the number of people being born equals the number of people who are dying. Okay? And therefore, I can go back and use my old example saying the n is fixed, the total population size is fixed at any time, because as many people are being born as are actually dying. We will come to an example where we have to relax this approximation a little bit as we go on. Okay, so now you are expert at this, you know how to calculate a reproductive ratio, you know that you have to look at the I equation, you know that you have to set S equal to 1, you imagine that I is small and then ask, is I growing or is I becoming smaller? So, the only terms of importance here are the beta S, the gamma and the mu. Now, the mu is a new addition that comes in here, assume S approximately equal to 1, R naught is beta divided by gamma plus mu. Okay? So, what is that saying? That is saying that R naught is shifted by sort of vital processes which are births, and it's actually decreased over the value that it had without birth. Sorry, go ahead.
Sir, would there be a dimension mismatch?
No, because mu,
if it is not product with
S, I and T are dimensionless because they have all been scaled out. They are numbers between 0 and 1. Even if I assume that they were just numbers, it's still dimensionless. It's just a number. So, therefore, this mu and this mu have the same dimension. Okay.
It is representing some rate. So, its unit should be per time.
That's right, it is. So, it's actually per time here. It's also per time here. It's the same thing because S has no dimension.
So, why you are not putting that it should not be put because it will become 0. But why with birth there is no S product with, but with death it is product with?
Because the number of people who die in a small interval of time dt is exactly mu times S times dt. If each person has the same small probability of dying, the number of people dying must be proportional to S. Suppose I have 100 people and there is 1% probability that some of them will die in the next 1 hour. Then in 1 hour I expect 100 to become 99. If I have 1,000 people in the same probability, the 1,000 people will become whatever 1% of 1,000, which is 10, so 990.
So, why same thing is not going with birth?
Because the birth does not depend upon the number of people who are there. Now, that is a slight exaggeration because you know that birth you need a father and a mother, so they must depend in some way on the people, but we are going to ignore that particular sort of thing as a detail and say that how, it doesn't you can sort of imagine that people are being created out of the air and just add it up.
Can it be thought about mu and
So I could do that, but that's basically saying mu into 1 is the same as mu. So I mean the way I've sort of normalized things. So it does, I mean I can get perfectly by saying that look, people are born at rate mu into susceptible compartment. And in a sense it doesn't depend upon the total number, they are just born at that point. The point is, that's actually an interesting point that I have not seen mentioned anywhere, that in principle you need fathers and mothers, so there must be some function of n must be sitting there, and if n is 10 million or n is 10, there should be a difference in the number of births, but these models don't assume that, they just assume that you are sort of creating people. Yeah. So as you know, R naught is shifted a little bit, and now you can say, all right, what are the steady states in the slightly more complicated model? I know I have R naught. Certainly one steady state is I equal to 0 and S equal to 1, R equal to 0, which is completely susceptible population. So if I set I equal to 1, R equal to 0, this becomes 0. If I set I equal to 0, I equal to 0, R equal to 0, this becomes 0, this becomes 0, this becomes 0. I just have the S term that sits here as 1. And if I set that equal to 1 with mu over there, it doesn't change, because it's mu times 1 minus mu times 1, which is 0. Okay. So that is the disease free equilibrium, but that is certainly a fixed point of these equations, but there is another fixed point. For example, if I wrote down, if I said di by dt equal to 0 to find the fixed point, I pull the I out, I get a term like this. I equal to 0 is certainly a solution, but beta s minus gamma minus mu is also a solution. So that's what this solution is. From here I can get the susceptible fraction as gamma plus mu by beta, which is 1 by R naught. From there I can put it back into this equation and get the I star, the fixed point value of I star, which is mu by beta times R naught minus 1, and the fixed point value of R star. And of course this plus this plus this must add up to 1. So it must be guaranteed that that is true. Notice now that this set of values is interesting. The earlier simple SIR equations, after the epidemic had run to time t equal to infinity, had no infected people left, had a small fraction of people who did not contract the disease, and everybody else was in the recovered compartment. If you remember, that was the structure of these equations. But once I allow for demography, once I allow people to be born and to die, notice now that the I term here, which is here, is now saturated at a fixed value. Look at what the S term did here. It fell down all this way at a little dip and then did this here. We will come back to this little dip and this increase a little bit later. And notice that the R actually did this, went up and also saturated here. But the important point to notice here is that even at t equal to infinity, that is in equilibrium or in steady state, there is always a finite fraction of people who are infected. This corresponds to a situation where a disease is endemic in a population. If you remember, we said the word epidemic, endemic, and we said the word endemic is used for the case in which the population, there is always a certain fraction of cases in the population who have that illness. So you can say yellow fever is endemic in parts of South America. That is what you mean. Mean that there will always be some background of level of cases of yellow fever in South America. Okay? You can say TB is endemic in parts of India, malaria is endemic in the Colaba part of Bombay, etc. That is what is meant by that. Means it's never, the number of cases never drops to 0. It's always some steady background value. Okay? All right. Having done that, let's get into the business of saying how do people who work in epidemiology or public health actually extract numbers that represent data. So one method is the following. Go back to these equations here. Di by dt is beta minus gamma minus mu. Combine these terms here, right? This is 1 minus R naught. Then integrate this to get di by dt is beta times, so again I can write it in this particular form here with R naught minus 1 with this R naught here. This is di by dt equal to something times I, which I can integrate to give I naught exponential of this particular term here, which I can write in terms of susceptible population times R naught minus 1 if I pull these terms out correctly, if I remember that this is the way I had to actually write it. So if there is some immunity in the population, then S is reduced from 1 to S naught, which I need to do in order to write that particular equation. How do real populations behave? If I imagine doing this in a simulation, I did it many times, but the simulation has stochasticity in it. That is, you are not guaranteed to get the disease from me. There is some probability that you get the disease from me. If you looked at this, the number of infectives here is a function of time. These correspond to many different ways of running, different initial conditions for running your experiment. So, in one condition you might go up and do this, one condition you might go up, all of them sort of show a peak and a decline, but each individual curve is different from any other individual curve. So, you should think of the SIR model as in a sense representing something that is some smoothed out version of these, it is somewhere in between here. So, if my population was infinitely large and I did an infinite amount of averaging, then I would expect all of these stochastic effects to vanish and behavior to converge onto the SIR prediction of a smooth predictable curve. And if you expanded this out here, if you looked at this particular part here, that really looks messy. You can see that some cases the disease actually went down because people did not manage to infect anybody before they actually recovered. So, that makes this estimating the initial rise. So, look at this I is I naught exponential of blah blah, this is believed to be true here at this point where it goes along. So, this is an exponential increase in the number of infected, which is what you see here. But to try and get numbers for R naught from data like this looks pretty horrible, which is why many people do not do this. It would be a natural thing to do, but it is very complicated because of inherent stochasticity in the data. So, this method works only for an epidemic and not for endemic cases. In early stages, the growth in infectious is highly stochastic and noisy, as you have seen there. And the other point is, unless it is a completely novel pathogen, people are likely to have some existing immunity in it, in which case you must estimate S naught as well. How many people in the population already have immunity? So, what is the actual susceptible population? And that is much harder to estimate. There is a second method, which is really a somewhat cute method. That is a very clever method. Remember, we are starting with these equations here, and go back to the old equation, which is the equation for ds by dt is force of infection times S. Okay. So, if I ask, if I put 100 people in the S compartment at time t equal to 0, that number will decrease, and it decreases at exponential of minus t divided by a time scale, and that time scale is the inverse of this particular rate. Lambda is the rate, 1 by lambda is the time scale, and that is the time scale that enters the exponential decay of this. From that I can calculate what is the mean time that people spend in that compartment. Some people will spend a long time, because all I know is the probability distribution of the time, and that mean time is 1 by lambda very simply. Okay. So, that is the time that you spend in the compartment. I can put my factors of beta, n and I. So, this corresponds to frequency dependent transmission. So, n over beta times I, and this is 1 over beta I star, where I star corresponds to the endemic equilibrium that I had earlier. Okay. So, I star is this particular quantity in terms of the S star, the fixed point value of S star, which I can write in terms of R naught, and here are the values of S star, I star and R star for the SIR model with demography, and this is how I relate the time spent in that compartment to the fixed point value of the number of infected people, which itself is a function of R naught. Is that clear what I did just now? Essentially all I am doing is finding out what is lambda. I know my expression for lambda from here, but what value of I should I use here? The value of I that I should use is the endemic value of I, which is I star, the number of people in the population who are infected. Once I do that, I can just plug this formula that I already calculated here into this equation to find out what the time spent there is. So, you should think of this as births coming in, deaths coming out. I imagine that I took one huge box and there I put my S, I and R in, and then I ask, suppose somebody is born into that box at a particular time, how much time do they spend inside the box? The individual who is born can do various things. They can be susceptible and remain susceptible all their lives, or they can be infected and go to susceptible, infected, recovered and then come out. Okay. But that is like saying exactly, remember how we balanced everything, the number of births balanced the number of deaths. It is saying you come in with rate mu and you leave at rate mu. If you think of this large box containing SIR, you can ask how much time are you spending inside the box. So, what is the interpretation of the time that you spend inside this big box with S, I and R? I have given you the answer on the it's your lifespan, exactly. It is how long you live before you die, the average amount of time is your average lifespan. Okay. So, that is related to mu, and 1 by mu is the actual lifespan. Mu is a rate, 1 by mu is a time. That is the interpretation. So, if I have a lifetime 1 by mu, I know the mean age of infection A is given by this particular quantity here, how long you take in order to get infected. You can then ask the question, what is the probability that a person is still susceptible at some age A? And that I can put on here because this is the mean age of infection. I exponentially get into that compartment. This probability is an exponential of minus A mu by R naught minus 1, and R naught minus 1 is approximately L divided by A. Okay. So, now I have everything that I really need. I can just go back and plot this particular curve here, and here I plot the basic reproductive ratio. Here I plot the mean age at infection in terms of years, and for different values of 1 by mu, 40 years, 60 years, 80 years, which is your lifespan, this is what the curve actually looks like. Okay. So, mean age at infection, the interpretation is when do you first fall sick. Notice that the larger your R naught, the earlier and earlier you fall sick. Okay. For R naught equal to 18, which is measles, let us say, you are typically falling ill at about somewhere around 1 year or 1.5 years here, as you can see. For R naught much small, you are much smaller than that, let us say 3 or 2 or something like that, you are typically falling ill by somewhere around 40 years or 35 years or something. So, that is really the reason why childhood diseases are not intrinsic to childhood. We talk about kids always falling ill with this or that. It is just that they tend to get caught earlier in life rather than later because they are highly infectious. Highly infectious meaning large R naught. Large R naught means mean age of infection is reduced, which means on average you tend to catch them when you are younger rather than when you are older. Okay. It has nothing specifically to do with the fact that these are children. How do we use that particular result? So, remember that the difficulty was that it was hard to estimate the number of people in the population who were actually susceptible, because people often have some prior, they have caught the disease when 20 years ago and they have forgotten about it. So, technically speaking, they should not be counted as susceptible population because they are immunized or they have already passed over into the recovered compartment. You should not count them. So, the way in which this is done is to use the following bit of biological or medical insight, that once you are exposed to an infection, you have very disease specific antibodies that are present in your blood, and you can be classified as seropositive or seronegative depending upon whether these little pieces of protein are in your blood or not, and that is something that a blood test can pick up. It is more complicated than a regular blood test. It has to be a test against certain antibodies that are present, but in principle, if you knew how many people in your population were seropositive or seronegative, you can infer from that what is your susceptible population, S naught. So, remember that S is 1 by R naught. You have to take account for the fact that usually this increases with age, the sample must be representative of the population, etc. You should not just take people in one school, you must take people across the whole set of ages. And the way this is done is, suppose you take a population from which you take seronegative samples from individuals of ages A1, A2, A3, A4, and seronegative samples from individuals of ages B1, B2, B3 and B4. Then you say, what is the choice of R naught given this particular, each individual is independent, each of them contracts infection at a particular age. So, given this multiplied across all individuals, what is the best choice of R naught? So, this is a standard likelihood maximization, a standard trick that is used in statistics, that says it is most likely or most probable that R naught is the value for which this particular quantity L achieves its maximum. So, with the data that I have on seroprevalence, I can go back and use a standard calculator and figure out what R naught was for a particular disease. Are you all with me so far? Any questions at this point? All clear? Yes? Nobody is blank. Okay. So, let us now move. So, what all did we do so far? We thought about how does one, we took a little detour into practically how do you estimate the value of R naught. We said the naive way of doing it, which is determine the exponential increase in the number of infected cases at the beginning of a disease, is probably a bad idea because it's very noisy typically, depending on the quality of your reporting. Then we said the better method is to just look at the population and ask what is the fraction of the population that has antibodies against, developed antibodies against a particular disease, and ask what is the seroprevalence of that disease within the population. Once you have that, you can use statistical tricks like the one I just told you to maximize the likelihood to find what is the best value of R naught consistent with the data that you've actually gathered. Okay. Let's now go deeper into asking properties of those equations, and in particular we want to ask why is it that the susceptible population came down, showed a little dip and then went back up again. That's something that we had not seen earlier, that hint of an oscillation, where it actually comes from. So to do that, let's think about how you approach equilibrium. Remember that was at short time, the curve came down like this and then flattened out. So these are questions about approach to equilibrium in the SIR model with demography, which means a set of equations that look like this. We had looked at these equations and we determined the fixed point of these equations. One fixed point, which was the unstable fixed point, was the point in which everybody was susceptible. It was unstable because the moment I put in an infected individual into that population and R naught was greater than 1, R naught divided by beta divided by gamma plus mu, then the number of infecteds increases, the number of susceptibles came down. So it didn't tend to go back to that earlier situation, it tended to move away. And where it moved away to, if R naught was greater than 1, was the endemic fixed point, where at long times I always have a fixed fraction of people infectious within my population. So that's what I want to understand. How did that come about, and how do you approach the endemic state? So the way that one normally does it is, for any set of variables ni, n1, n2, n3, etc., we are always thinking of equations that look like this. Okay? The fixed point value of these equations is the one for which dni by dt equal to 0. And so that sets some constraints on n1, n2, n3, n4. It identifies what those values ought to be. The stability about that fixed point is determined by the matrix or the Jacobian of this form. So the first row is delta f1 by delta n1, delta f1 by delta n2, and the stars say evaluate that at the particular fixed point that you want to consider. So as I said, here is what you have to do. Let's go back to these equations and actually do it. So one derivative with respect to, let us say, s here picks up this value, the beta s and the mu, and they have to be evaluated at the star. So I have beta I and mu evaluated at fixed point I star. The second term here is the derivative with respect to this thing here, no? Which is the term that enters here. This is the 0 here. I can go through this exactly as I have written it out here and compute the Jacobian. The next step is to ask, that determines the stability of the fixed point, is to say what are the eigenvalues of this particular j. For a matrix of this form, I know I calculate the determinant, I put a minus lambda, minus lambda, minus lambda here, calculate the determinant, which is really finding the solutions, the 3 solutions, the 3 by 3 matrix of this particular equation here. Okay? So this is a cubic equation, has this particular structure, but notice that this term and this term are common. Okay? So one solution automatically is a solution which lambda equal to minus mu. That's one. That is a negative eigenvalue. Therefore, any perturbation about any of those fixed points, either the completely disease-free fixed point or any other new fixed point that you will try to find, will be, or this endemic fixed point will decay. Sorry, let me take that back. This is calculated only for the endemic fixed point because I put the stars in there appropriately. I expanded about that particular point. Okay, so this is the eigenvalue that is always real and negative, and there are 2 more eigenvalues that follow from the solutions of this part of the equation. I sort of imagine that all of you have already done things like this, so it's really not a problem. You can look first at the disease-free equilibrium where I equal to 0, s equal to 1, and calculate lambda 1 equal to minus 1, lambda 1 equal to minus mu, no? Yeah. Lambda 2 equal to mu, lambda 3 equal to beta minus mu plus gamma. So now the question is, at what point is this less than 0 or greater than 0? So the condition that, so I'm not sure, maybe there should be a minus mu. I think it should be a minus mu. I think I made a mistake there. Yeah. So the condition that all of these eigenvalues be negative really comes down to the factor, is this particular quantity negative or positive? Whether it's negative or positive comes down to the factor, is beta divided by mu plus gamma less than 1 or greater than 1? But this of course is just my R naught. So we've come back to saying that, look, whether R naught is greater than 1 or less than 1, it really determines stability about the disease-free equilibrium. Okay, so that was the disease-free equilibrium, and let me just look at these equations again. Can you see whether my sign is right or wrong? Yeah, it has to be minus mu, because here if I put lambda equal to minus mu, then this quantity is automatically 0. Yeah.
If it is not minus 1, then there is no analysis with respect to R0 because it will become unstable in that.
Yes, that's sort of reasoning backward, is just looking at these equations. So it has to be minus because this quantity has to be 0. If I choose that to be minus mu, then minus mu plus mu will be 0. Okay. So now we can look at the endemic equilibrium, and there I put in the values of S star, I star and R star. I put them back here. And I calculate it. As I said, this is now a complicated quadratic equation. It usually does not have much insight. You can write it down and calculate it by hand if you wanted to. But a nice approximation is one in which you ignore mu R naught squared. Often that is the right approximation to make. And then lambda 1 is always of course equal to minus mu, but lambda 2 and 3 take this particular form. It is minus mu by R naught by 2. So that quantity is always negative because mu and R naught are always positive. But this term here is a sum plus or minus of a complex part, which is I divided by square root of AG, where A is this form and G is this form here. It just follows from analysis, which you can actually do. So what is this saying? The real part of all of these eigenvalues, sorry, this should be capital lambda, not small lambda. The real part of these eigenvalues is always negative. So finally behavior will damp out. However, the fact that you have eigenvalues that appear in complex conjugate pairs suggests that the approach to that can be oscillatory. Yes? No? Yes?
So what was the question?
Wasn't a question, I was just sort of checking for that everybody was awake and ready. What is the implication of having a Jacobian with two eigenvalues that appear in complex conjugate pairs? The interpretation is that this leads to an oscillatory solution, which is finally damped out by this term here. So it goes to a constant value at long times, but the approach to that constant value can have oscillations inside. So let's look at what the full bifurcation diagram looks like. So of course there is nothing, this is infected fraction less than 0, so that's not physical at all. Let's just ignore it, it's just drawn here. If I go above this, there is depending upon the contact number, which is R naught, whether it is less than 1 or more than 1, I can either have a stable disease-free equilibrium or an unstable disease-free equilibrium. But this will move to the stable endemic equilibrium marked by this line, where there is always some fixed fraction of infectives at this point. Okay. How did I say that this is approached by oscillatory dynamics? It is easy to plot this, and this is what the solution looks like. So for some set of parameter values that are 1 by mu 70 years, beta is 520 per year, 1 by gamma 7 days, some initial conditions, etc. So very small number of infectives, S naught is some particular value here. You can see that the fraction of infectious people is oscillates until finally at long times. So this is time in years, this is the structure of that oscillation. This basically becomes a constant. So it approaches a constant value asymptotically through these oscillations. Here is a plot of, as you change the gamma, you change the beta, how does the period of oscillations change? You can work all this out. Basically, you can just calculate this, or put it on a grid and calculate each of these values over here. So this line here is the line where you have an R naught of 15 as a function of the combination of these variables here, and you set 1 by mu equal to 70 years. Okay, let's just recap model so far. We've looked at the SIR model. I mentioned the SIS model. We looked at susceptible, infected, recovered, back to susceptible again. We looked at susceptible, exposed, infected and recovered. All of these are models I introduced you in the beginning saying This is how we're going to think about is what an exposed class is. Some people who are susceptible can go back to being, who are infected and then recovered can go back to being susceptible because their immunity wanes and so on. Let's now make an even simpler model, and that's a model where you're either susceptible or you're infected. Okay? So, ds by dt is minus r times I times s, di by dt is plus r times I times s. So, s plus I is n given here, and now I can take this, take s equal to n minus I and put it back in this equation, this particular equation here. Then the equation that I get is di by dt is r times I into n minus I. So, there is both a linear term and a quadratic term that damps down with a minus sign. This is of course the famous logistic equation, which you will probably see much more next week. You have already probably seen it today as well. Okay? This is what the solution to these equations looks like. As I said, start with initially susceptible, initially infectious. Everybody gets infected, nobody remains susceptible. That is a natural progression of this particular choice of model. Let us go back and do some algebra with the SI model. So, here is our starting equation. I can take that, bring this factor of I into n minus I down here, dr by dt is r, take the t to the right hand side, integrate both sides between I naught and it, between 0 and t, and finally wind up with an equation that looks like this, which I must evaluate between time t, infected at time t equal to 0 and infected at time t. I can write it in that last particular form that I wrote down in the bottom, and then I can take this and actually solve this. So, because it is a logistic equation here, it actually has an analytic closed form solution in that form. So, that is a solution of this equation here. It can only involve r and n. It involves only r and n, as you can see here. Okay? I can make this equation a little bit more complicated, but instead of having I here, I have I divided by n to the power p. I can always pull the n factor out somewhere here and write this as be kn, no, I think that is correct, no. Yeah, should be right. So, I of t now has this particular form, expression minus pkt whole raised to the power 1 over p. It is just a slightly more complicated form, but sometimes when confronted with real data for the number of infected individuals, etc., that looks like this, this form sometimes does a little better than that other form. None of this is sacred or anything. People choose, make approximations, choose the forms of models that correspond to things that they think might more reflect reality than other types of models. So, I do not know what particular realistic assumption goes into thinking of that, but again that is a model that happens to be solvable in terms of the number of infected at a particular time. Here is our second model, which is called the SIS model, and that is where an infection does not confer immunity or your immunity wanes. Okay? So, ds by dt is gamma times I minus beta times s. This is the re-entry back into this compartment, and this is the leaving of this compartment here. And I think there is probably a missed sign between here and here. There should be a plus sign here, if this is a minus sign. Okay? Here are properties that I can figure out for this model. What is r naught being beta by gamma? But in what limit would I think of an equation like the SIS model? What are the diseases for which the SIS model might be valid? Usually these diseases tend to be sexually transmitted diseases such as gonorrhea or chlamydia, because typically having once recovered, you can be infected again. The common cold is also like that, but also partly because the common cold virus mutates fairly fast from year to year. So, even though your symptoms may be exactly the same as last year or the year before last, there are subtle differences in the virus that gave you the common cold which can change. So, we interpret that as saying generically you have got a cold, so you generically go back, you are never really completely, you should technically have been recovered, but you are actually susceptible. Here is another version of SEIR with demography, so that is with births and deaths. And typically you would use these models in situations where you have a long incubation duration. So, you are exposed, the virus or bacterium is multiplying inside you, but you are not capable of infecting other people yet. So, the individual is infected, but not yet infectious. So, what examples? Chickenpox and dengue hemorrhagic fever have a long incubation duration, where the individual cannot yet transmit the pathogen to other people. I'm not spending much time on it. I just want you to look at the structure of the equation. Again, it puts in the mu here, the mu e, the mu I, the mu r, sort of then all of these can cancel out. This is the term that is minus beta s, the usual term here. The minus mu s is the deaths from the S category. So births and deaths balance out. If you add all of this, the sum of this must equal 0, and that's by design. Okay, clear? You should be able to write down now any sort of equation. If I give you this is the scenario for what is happening, you should be able to write down a set of compartment equations that refer to that. So the SEIRS model again has a sort of oscillatory approach to the endemic equilibrium. The SIR model, of course, as we showed, came straight down over here, was uninteresting from that point of view. And the SIS model, you pretty much go, you fall sick, and then you sort of stay there. Let's talk a little bit about carrier states. And the carrier state is one in which you can go from susceptible to infected, but infected can be, you can move either to become a carrier of infection or you can recover from that infection. A carrier of the infection is someone who remains infected but should be in a different compartment because they are not showing any symptoms or signs of being infected. So they are unaffected by the pathogen but can transmit it to others. And this is important in the transmission of disease such as typhoid, Clostridium, influenza, HIV, etc. With HIV, you can sort of seem normal for a long time, especially if you have under medication or something, but you can still be in a position where you can transmit the disease to other people. I mentioned typhoid Mary, as so there's some history, you can go back and read it on Wikipedia, etc. So she was an asymptomatic carrier for typhoid fever. She was a cook, as I mentioned, and although she appeared perfectly healthy and functional, she infected about 50 people before she was finally quarantined. They said that, look, you cannot do this anymore. I think they put her in jail or made sure that she had no more contact after that. Here is how I would write the equations here. So here is where my carrier state appears at this point. And the quantity, there are new quantities here that come in. There is a quantity Q, that is a fraction of acute infections that become carriers. Epsilon is the reduced transmission rate from chronic carriers to acute infected patients. So look at why we had to do this. Infected people transfer the disease at some rate beta, but carriers can transfer it at some other rate. They can still transfer, but it need not equal beta, okay? Because whatever is doing to them, they need not have the same viral loads as the regular people who are, but the virus has not gone out of the system completely. It has not been flushed out. So that's where this term epsilon comes in. That's where the term Q comes in. So the fraction of acute infectious that can become carriers that enters here in this particular form. And the rate gamma is a new rate that tells you the rate at which you leave the carrier class. You also have to worry about the rate at which you enter, the rate at which you leave, and that's where the gammas enters, both here and here, and they cancel out between carrier rate of change and recovered rate of change. Everything that we did with the earlier set of equations we can actually do. Here are those equations again, and here is the R naught. And how do you calculate R naught? Same trick. Assume small fraction of S equal to approximately 1, infected equal to approximately 0, etc. How do things grow, combine terms, etc. You get R naught to have this particular form. How do you calculate the fixed points, the non-trivial fixed point? Again, look at where all the left-hand sides equal to 0, solve a set of algebraic equations together, and you wind up with a complicated relation of this form. I don't want to do this because it's just mathematics that all of you can do well enough at home. Let me just do last one or two more things, and then we'll stop. One thing I want to tell you a little bit about is infection-induced mortality. And that's because that introduces a new twist into what we've been saying so far. So far, we constructed models that ensured that the population size was the same. Okay? We said there are a certain number of people being born, there are a certain number of people dying, and if you balance the number of people being born and the number of people dying, then that ensures that S plus I plus R must equal to 1, even with demography. But are there situations where you have to move away from this particular limit? So one way to do it is to say that, look, if an individual acquires an infection, they may die of that infection. Okay? Some people will recover, but some fraction of them will actually die. You might think that one simple way of doing it is just to say this is minus some rate m times the number of I. That is correct, but it's usually a little better to think about it as the probability of an individual in the I class dying of an infection before either recovering or dying of natural causes. So how would I write those equations again? I would say ds by dt is people being born, people being this thing, people dying here, and this last term here is the fraction of people that die from the infected class. So that's why there is a minus sign here. If rho was 0, I could forget about this. There's no fraction at all that dies from here, and this just reduces to the standard birth and death equation, SIR equation with demography. So this is rho into 1 minus rho term that determines what is the fraction of infecteds that actually goes and dies and removes from your population. With these equations here, you can check that the number of people doesn't remain constant anymore, the initially chosen value of n, because I have now allowed people to leave from this particular class. Okay. So this means that your population size can vary. That's important because for the following reason. The population size entered our definition of the force of infection. In one case it entered explicitly, in one case you didn't see it at all, and you got equations that looked kind of the same but were for slightly different quantities. One was for the fraction of people in SI and R classes, one was for the total number of people in SI and R classes. And the lambda, the form of the lambda differed between these two choices. So let's just take these equations here. I've just sort of sorted it out a little bit, and let's start with density dependent transmission. And if you do that, you can first ask, all right, what is a disease free state and what number n does that correspond to? So over here, setting the disease free state is of course setting no i's, no r's, getting rid of various terms here, everyone is acceptable. So the balance between nu and mu, which is nu minus mu n, sets the value at which n sets the n star value over here, which corresponds to the disease free state. Okay. I can also look at the endemic state for these equations, the SI and R equation, that is S star, I star, R star have this particular form. Again, this is just a question of actually sitting and working out these equations. So once I have that n star here, I can now say, so this over here was for the disease free state, this is for the endemic state, but in the endemic state n star is also changed. Okay. Once I do that, how do I calculate n star? I basically calculate S star plus I star plus R star, which is the total n at a particular point, and that's what this corresponds to. If I set rho equal to 0, then various terms cancel out, they are not cancelled out. It reduces to what is called the carrying capacity, the actual number of the disease free state in this particular case. Okay. So now I know what happens to n star, now I know what happens to I star, R star, S star, etc. Now I can try this with frequency dependent transmission. So now I have these additional factors of n that come in here, and then I can ask, okay, I have a value of n star that corresponds to disease free state, which again remains the same because it doesn't involve the beta term at all, but then my other numbers sort of change because now these equations here are slightly different. Here are basically just results here. So for both frequency dependent and density dependent transmission, the population size is reduced by allowing people to die. Okay. Provided mortality is low, provided that factor of rho is small, these assumptions lead to similar results. Both, so there are two curves sitting here which you can't see for value of rho equal to 0.1, both for pseudomass action and for mass action. The larger that rho is, these curves begin to look very different. So this is rho equal to 0.9, and this is one curve here which is the pseudomass action curve, and this is the real mass action curve. Pseudomass action is the same as I called whatever density dependent transmission, and I think just, all right, whichever one is which. So when mortality is high, frequency dependent transmission leads to the largest drop in total population size, and that's because the pseudomass action, which is density dependent transmission, says that as you decrease population size, the contact rate itself decreases. Remember, because the force of infection has a factor of 1 by n inside it. Okay. Because of that, you tend to infect people less, so your numbers don't change all that much. Okay, we do a little bit more. I have a few more minutes left. Let's just talk about seasonality effects, and then I really will stop at that point. if you remember the data that I showed you in my first talk, we were looking at measles epidemics in various countries, Australia, the US, etc. And I pointed out the fact that they had these nice peaks that seemed sort of roughly equally separated. So I said this is something we'll return to later, trying to understand why is it that you can have seasonal epidemics in a particular disease. What is the reason behind that? So the causes of seasonality, for example, is you can think about what all they could be. One is certainly, if you're talking about measles, measles has a large R naught. The larger the R naught, the earlier the age at which you catch the infection, typically between 1 and 2 years. That's usually when children are in school. So the moment you have one infected child with measles inside a school, everybody gets measles at that point. But children meet only during school hours and school terms. So there are 3 months in the summer where they don't meet, 1 month in winter where they don't meet, etc. But when they're in school and all together, that's when the infection has the maximum chance of propagating from child to child. The other issue is survival of pathogen outside the host, which is again could be seasonally dependent. For example, you see winter peaks in gastroenteritis because the rotavirus and norovirus survive better at low temperatures. The low humidity increases the survival of influenza virus in air, again something that I didn't know, but I just found out recently. The nature of vectors and non-human hosts also depends upon season. So for example, Lyme disease, which is a disease contracted by ticks, is often a problem as occupational hazard of hiking in North America. But if you ask when can you hike in North America, the answer is you certainly be dumb to do it in winter. It's the summer months that people tend to go out, climb, walk, etc., etc. So that's where seasonality of Lyme disease transmission comes in, because that's when you tend to encounter more ticks outside. Also seasonal changes in human immune competence. There are just times when your immune system functions better and times when it functions worse. This is also a function of season. You have own bodily clocks that determine the levels of for example, immune molecules in your system. All of these are actually important. Here is some data for chickenpox, measles and mumps from Copenhagen sometime in the 20th century between 1940, 1930 and about 1965. The way one does that is the following, and this should be obvious to you by now. You take the SIR model with demography, but the beta term, which is the term that tells you how you transfer infection to other people, you can now make time dependent. Okay? So if beta is small, beta of t is small, then the probability that you will infect somebody else becomes small. If beta of t is large, the probability you infect someone will become large. So the largest and the smallest values here are where sin omega t is 0, so beta t is beta naught, and sin omega t is 1, which is beta t equals beta naught plus beta naught beta 1. Okay? So it sort of oscillates between those particular regions here. So from here I can say there is at least some definition of a yearly average basic reproductive ratio, which is beta naught divided by gamma, but depending upon the value of beta 1, it can be greater than that or even lesser than that. So it can be a fluctuation above that particular point. So you can take these equations, take the unforced equilibrium state, expand about that, you wind up with differential equations that tell you about the nature of fluctuations, and that's a complicated calculation by Bailey in 1975. But the results are interesting. So the results were the relatively small change in the transmission rate, that is beta 1, beta naught is 10% of beta naught, let's say. That can lead to very large changes, as much as 78% in the number of cases of people reporting with infection. So the interesting thing about seasonality is that small changes, small fluctuations about a steady, even low value can lead to a large amplification in the number of cases. Here is a second interesting point, that if you go back to our old curve, which showed you what the oscillatory approach to equilibrium was, it turns out there is a natural period in this. Okay? So that's this point between two peaks in this. We worked that out, or at least I showed you how it could be worked out in terms of the time period 2 pi by square root Ag, where A and G were related to things like mu, gamma, R naught. So given a disease, given a mu, given a gamma, given an R naught, with demography, with vital dynamics, the settling down is a function of all of these quantities. Now I can say that, look, I am going to perturb the system by some seasonal perturbation, but that can be different from the natural frequency which the system likes. So this is the natural frequency, but on top of that I am putting my perturbation frequency, which is my beta of t. And then something interesting turns up, something called harmonic resonance. And harmonic resonance is familiar to anyone who has pushed anybody on a swing. You notice that there is sort of natural frequency at which you push somebody on the swing so that they build up. They start off small, you keep pushing, it sort of moves larger and larger and larger and larger until finally the kid is practically flying off. And all you're doing is giving a same small push. It's not a large push, it's a small push, but it's calibrated at the frequency, the natural frequency of the child plus the swing. So if you perturb the system with the beta t and a frequency that is close to the natural frequency of the SIR model with demographics, you can increase the amplitude substantially exactly at that point. So now you can go to the diseases, measles, chickenpox, rubella, etc., and say, okay, I can figure out what the natural frequency is. This is the period at which I will force it. And you can see that for each of these diseases, there is some characteristic period at which if you force, you get the maximum number of cases that actually turn up. So now the question is, what does seasonality do? Where is it in this curve? Is the seasonal forcing somewhere here, or is it optimized to be somewhere near at that particular point? And that again has an interesting evolutionary impact, because then the pathogen wants to maximize its chances for survival. So how does the pathogen tune its dynamics in such a way that it can do things like that, can adapt to any exogenous or outside forcing that comes from? This is also interesting because this is now a fairly nonlinear problem, and you can sort of force it at some different rates and look at what happens. You can even get behavior that doesn't has a cycle that is more than a year, even if you're forcing it at a period of 1 year. So your system response can be at a smaller frequency than the frequency at which you're pushing it. Because this is a nonlinear system, it can respond at multiple frequencies. So that gets into a little bit of the technicalities of how you think about this from a dynamical system point of view, but we won't worry about that at this point. We just stop here now. It's time now for. So thank you. Any questions? Or there will be time to deal with questions anyway tomorrow. Yeah, go ahead. No biological reason. In fact, a slightly later this is a slightly different